We're so glad to have you here for this distinguished lecture today with our esteemed guest, Dr. Brian Anderson. He is the director of the U.S. Department of Energy's National Energy Technology Laboratory, and he'll be talking more about that during the course of time. But there are 3 sites for NETL. One of them is here in Pittsburgh. It's just south of the city in South Park. He manages the complete NETL complex, including delivery and execution of the laboratory's mission and the national programs in fossil energy. He previously served as director of the West Virginia University Energy Institute. He has a long history of collaboration with NETL and other DOE national laboratories. Brian served NETL as the coordinator for the International Methane Hydrate Reservoir Simulator Code Comparison Study. And in 2011, he received the Secretary Honor Achievement Award from the Secretary of the DOE for his role on the Flow Rate Technical Group, a team spanning multiple national labs that worked in response to the Deepwater Horizon oil spill. Brian also received the Presidential Early Career Award for Scientists and Engineers, the highest honor bestowed by the U.S. government on science and engineering professionals in the initial stages of their careers. So without further ado, I'd like to introduce Brian Anderson.
First, let's see, how's that? I'm usually a pretty loud talker, and so if I put it too close, it might be too loud. So first, I'd like to thank Anna and Jay for extending the invitation. I was really excited to come to CMU. There are a lot of familiar faces in the audience that I know from a pretty recent past at West Virginia University, and I'm extremely excited to be at NETL and be part of that NETL team. As CMU knows, and I'll talk about a little bit about the history, but the history of the National Energy Technology Laboratory is intertwined with the history of energy research at Carnegie Mellon University. And so that certainly plays a role in the legacy, and it does because of the fundamental directions that research goes at the university and the National Laboratory. They have not diverged much at all over the 100-year history of the collaboration between these 2 organizations. And so it's really important for me to be here and really excited to talk to you about some of the things that we have going on at the lab, programmatic directions, priorities among fossil energy in the Department of Energy, and hopefully build some new and deeper relationships. Let's see, I have a pointer here. And so, not to be too grandiose in the vision and where we believe the role of the National Energy Technology Laboratory is in the future of our energy, but I will say that the future of the globe is on our shoulders at NETL. Just, I won't overstate it at all. But globally, we use a predominance of fossil energy, and we are faced with the changing climate as a result of human-induced carbon dioxide emissions. And therefore, those 2 things coming together means that the technology solutions that will come for the future of energy that's deployed globally is being developed here at the National Energy Technology Laboratory and with our partners. And so, no pressure. I'll just say it, there's no pressure on us at all. And so, to that point, this is the EIA's assessment in 2017 of our energy use in the United States, primary energy fuels on the left, and our uses on the right. And as you see in the power sector, 2017, between natural gas and coal and that smidgen of oil that's used for power generation, is about 60% fossil energy, 30% coal, 30% gas. There's a carbon footprint associated with that. In the transportation sector, while the fleet is electrifying, it's not electrifying too fast. We're at 95% is fossil energy, and a considerable bulk of that 5% remaining is biofuels, quite frankly, and that's because hydrocarbons that we store in our gas tanks provide a very dense source and flexible source of energy to provide in the transportation sector. Now if we start shifting and electrifying that fleet in the transportation sector, well, it's going to move down to power if we're electrifying it. Yes, we can be quite a bit more efficient with electric motors and plug-in hybrids and things like that. But still, there's a humongous component of fossil energy, and keep in mind, this is just the U.S. In the industrial sector, about 88% of the energy used in the industrial sector is fossil, and then same thing in residential commercial for heating and things like that. And so fossil is a humongous part of our current energy portfolio in the United States, and is likely to continue. And so it's incumbent upon us to step back and look at what happened during the Clean Air Act, and afterward how the emissions were cleaned up, and take an example that technology can provide solutions, and that's where we are, the National Energy Technology Laboratory. When we look globally, just from a markets perspective, there are still approximately 1 billion people without electricity on the globe. There are health outcomes associated with the access to clean energy as well. And so when we look at the deployment of new energy technologies around the globe, it is my belief that the United States should continue to develop technologies and lead in the decarbonization as well as the efficient use of the resources around the globe. So the priorities, as set by our current Assistant Secretary for Fossil Energy, Steve Winberg, a Pittsburghian, I might note, are as follows. So these are the evolving priorities of the Fossil Energy Office. First is develop that coal plants of the future, and it's, again, not just for deployment in the United States, but deployment around the world. And so as you may have seen, there was an RFP that was on the street a couple months ago to build, called Coal First, stands for Flexible, Innovative, Resilient, Sustainable, and Transformative. And, sorry, I have to remember it. And that is specifically trying to break the mold of the current fleet of coal-fired generation to look at, as mentioned, flexible. Can it be flexible in terms of meeting grid demand that cycles and operates in a dynamic manner, as opposed to the 1970s 1 gigawatt power stations that operate on baseload? Innovative, of course, it needs to be innovative in order to be the coal plant of the future. Resilient, again, fits that model of the changing dynamics of the grid to where it can be resilient with the ability to store on site the fuel for a number of days to months, but also be resilient to change in the dynamics of the grid and delayed interfaces. And then transformative part of it is that the megalithic gigawatt-sized power station, as we look at the way that the grid will operate in the future with a larger mixture of variable generating sources, can you build a smaller, more modular system that can take advantage of microgrids as well as distributed generation to an extent, and operate somewhere in the range from 50 to 350 megawatts as opposed to the larger power station. So that's a number one priority for in the coal plants of the future for fossil energy, but also how do we modernize the existing fleet? There's a lot of capital already sunk, a lot of construction, and billions and billions of dollars worth of capital that's already in deployment around the United States. And so if we can affect how to modernize that existing fleet through retrofits as well as efficiency improvements, every ton of coal that you save by efficiency improvement means almost more than a ton of CO2 for sure. And so as we look at different options to modernize the coal fleet, that is also wrought with its own constraints technologically as well as economically and from a policy standpoint. But it is absolutely essential. The third priority is one wouldn't have to strain too hard to guess, is how we lower the cost of deployment of carbon capture, utilization, and storage through CCUS. And this is not just carbon capture and sequestration, but there is a heavy emphasis on utilization as well. Certainly there are tax credits, the 45Q that operates and allows for tax credits on the utilization for enhanced oil recovery, but we want to go beyond that. Thermodynamically, and just as a background, if you don't know, I'm a molecular thermodynamicist is how I would have always described myself. And so I'm intimately familiar with the free energy and the free energy barrier of taking CO2 and moving it into something more useful. But there is tremendous efforts to lower the activation barrier through catalytic methods, electrocatalytic methods, as well as using photo catalysts to beneficiate CO2. And so that's also a big priority. The fourth priority I'm listing here is advancing big data. And so while that might have been over the last, well, I'd say almost 10 years now, certainly a buzzword, big data. We are serious about it in the department. In fossil energy, we're serious about it at the lab, so much so that we are investing more than a couple $1 million in a data analytics facility on the campus here in Pittsburgh. Because there, as we develop more and more sensor capabilities, more and more data acquisition capabilities across the entire portfolio of fossil energy and energy writ large, there is truly an opportunity to try to take that data and learn from it. And so as we develop the algorithms through artificial intelligence and machine learning to be able to cull all of that wealth of data to learn from it, we want to capitalize on that. And so that's why we are investing heavily in our advanced in big data, data analytics, and machine learning capabilities of the laboratory. The next to last is in that energy-water nexus. If you're not familiar with the amount of water we use to produce electricity through thermal generation, it is an astounding amount of water globally that is used, most of it freshwater. And so when we look at the way that we impact the environment through the deployment of fossil energy technologies, we cannot overlook nor overstate the impact on our freshwater resources. In this region, we're blessed. We have really robust river basins here in the eastern part of the United States, but globally and even in the western part of the United States, it is not to be understated that impact that we have on that water system. And so the Fossil Energy Office, in collaboration with EERE and other offices across the department, are really focused on improving our and adding efficient uses of freshwater and not freshwater resources in our electricity generation. And then finally is revitalization and retooling and maintaining readiness of our Strategic Petroleum Reserve, which is also under the fossil energy portfolio as one of our sister programs. So to give you that grand vision of where we are going in the fossil energy space, now I'm going to focus on NETL, our role, our partnerships, and where NETL is going to be going into the future. And so we are really owning our mission. And that mission is not only in technology development, employment, but it's about how we integrate and discover and mature new technologies in the fossil energy and energy space. And the reason I love this mission, which pre-existed me, absolutely, the mission is to be able to take technologies from the laboratories that exist at NETL, from the laboratories which we may discover new technologies, and our partners that are our local and regional partners, academic partners, industrial partners. If you look, we have 900 projects in the United States right now. And how do we take the technology developments out of all of those partner projects and then move them into the market? Because the one key word I would like for you to take away from at least where I believe we should be going at NETL is impact. We want to have impact into the market, not just, and I'm an academician, I can admit this. At least historically was an academician. Sometimes we do research without impact. And right now, we can't afford to do that. Time's moving forward with or without us in terms of how we develop technologies and deploy them around the globe. And so we are trying to focus the portfolio on how technology development moves into commercialization and has impact on people's lives. in the United States and across the region. We want to be known, and I believe we, in some circles we are known as the fossil energy research resource for the United States and for the globe, whether it's in-house or through our partnerships in which we fund research, that we are the central point of technology convening in the fossil energy space, and that we both generate new technology and new information, but we are a steward of that, and to try to help, again, go back to deploy and create impact from the technologies that we're working on. If you're not familiar with NETL, we are one of the 17 U.S. Department of Energy national laboratories. Of the 17, 10 are in the Office of Science. Those are the ones, largely a lot of them have light sources or neutron sources or something. That's the Office of Science laboratories. There are 3, we call them a weapons lab, the NNSA laboratories, historical from the Manhattan Project, and then 3 applied national laboratories. That is the National Energy Technology Laboratory with a focused application area in the fossil energy space, NREL, the National Renewable Energy Laboratory in Golden, Colorado, focused portfolio, focused more on energy efficiency and renewable energy, and Idaho National Laboratory, which is our nuclear lab. And so those make up the 17 national labs. Well, one thing that makes NETL unique, and some of you may know this, and it might be a positive or a negative, I'll leave that up to you, but we are the only government-operated laboratory of the 17. All of them are government-owned. We're the only ones where I'm the only national laboratory director that's a federal employee. Now, this gives us a very unique insight into the direction of energy policy, the direction of the Department of Energy, but it also gives us an opportunity to be able to take and capture, and this is back to the technology steward idea, is that we manage the portfolio for fossil energy, and we also manage a large portion, the majority portion of the portfolio for the Office of Electricity and for CSER. That is, CSER is the Office of Cybersecurity, Energy Security, and Emergency Response. And so we're able to take technologies that are being developed at those 900 project partners around the United States and help chart a path forward for energy development. And that is a unique opportunity of us being a go-to laboratory. And so that is I think, a tremendous opportunity. So historically, say coal research began 118 years ago in Pittsburgh, Pennsylvania, on the campus of Carnegie Mellon University. Then it wasn't Carnegie Mellon, actually. Carnegie Institute of Technology. And to bring the 3 branches and the large footprint that we have in NETL, as Anna mentioned, we have 3 sites. One in Morgantown, West Virginia, one in Pittsburgh, and one in Albany, Oregon. In 1918, now 101 years ago, there was petroleum research that began in Bartlesville, Oklahoma. Historically, we had a site in Oklahoma as well. And in 1943, in the midst of the Second World War, there was a materials research facility in Albany, Oregon that began working with our Navy on submarine materials. In 1946, a syngas research gasification facility in Morgantown on the campus of West Virginia University, hence some of our ties to the local and regional universities. In 1977, all 4 of those, Bartlesville, Albany, Morgantown, Pittsburgh sites, joined the Department of Energy. In 1996, and some of you may remember, I actually remember this one, that the Pennsylvania and West Virginia sites formed FETC from METC and PETC. And then that charted our pathway on the National Laboratory in 99, and I'll skip in 2001, we have an Arctic Energy Office that supports operations in Alaska, and then Albany joined us 14 years ago, and we are the NETL that you know today. We have a field office in Sugar Land, Texas, that also supports some offshore drilling work and some of our work in related to Texas. So I've mentioned this 900 project number a few times, and that's just it's a number of scale to give you a sense of how many projects we're working on either internally at the laboratory or with our project partners. And that's a wealth of data, a wealth of knowledge and technical management that we have at the laboratory. All again, if we can call those together and look at the pathway forward, this really gives us a lot of insight in the direction of the future of energy. We have a little over 1,200 employees. These data, I think the one I saw yesterday is actually 1,282. because we do have a new research site support contract that started in January and are onboarding some contractors there. We have 3 labs across the U.S. and approximately $1 billion a year budget that runs in and through the lab that we manage. And this is broken up, our workforce, between contractor workforce and federal, as you see here, where the contractor workforce supports site operations as well as research site support, our 2 biggest site support contracts. And then within the federal workforce, a breakdown of the levels of education. As you see, we do employ a number of PhD and master's level engineers, scientists, and technologists. And then us being the go-go laboratory is the other unique aspect is we possess an array of authorities that the other national laboratories don't manage, in particular being able to program, plan, and develop and execute the program, the fossil energy program and vision that I mentioned on the first slide, as well as contracting authority that the other laboratories don't have. And that does present a bifurcated national laboratory, if you're used to working with some of the others, but we've managed it and we figured out the processes to make that clean. So if I focus specifically on the in-house research arm of National Energy Technology Laboratory, we have organized ourselves, and this happened about probably seven years ago or so, to look a little bit more like academia when it comes to the way that we organize our technical skills and technical staff. At a university, we're broken up into colleges and departments associated with typically the degree you have, or at least the skill set. And so we are as well at NETL. We're broken up into computational science and engineering. That's everything from high-performance computing and atomistic scale modeling through machine learning and data analytics. A strong materials division where much of the physical capabilities that we have that are unique across the United States are housed in Albany, Oregon, in the materials engineering and manufacturing space, but certainly materials is everything from structural materials to functional materials that one might think of as catalytic action or some sort of chemical action as a functional material. And so then the third pillar of our core capabilities is in the geoscience space. And we're increasingly seeing that, yes, most of our fossil fuels come from under the ground, which comes with a pretty substantial skill set across industry and across the globe for the understanding of subsurface processes that includes fluid flow and as well as geophysical processes that happen during the development of hydrocarbons that we can learn from and apply to everything from CO2 sequestration to geothermal production to nuclear waste storage. And so we are building on those capabilities in our geological and environmental systems. Energy conversion engineering is a historically very strong group of talented individuals at the lab that includes reaction engineering, and we have a new facility that just opened in Morgantown. We'll be commissioning here in the next couple months called REACT, which is a unique, really one-of-a-kind facility to be able to do automated reaction engineering, everything from catalyst development through different process conditions for reaction chemistries, and operate 24/7 unintended automated. And it is a tremendous facility that we're opening. In energy conversion engineering, also design, validation, and again back to innovative processes as a whole, including how we process water. And in systems engineering and analysis, we have a whole effort to now dive deep in a couple of these in multi-scale modeling, simulation, and optimization, where in fact one of the more successful tools that's been built at NETL and deployed across the globe is a computational fluid dynamics model. We also have called MFIX, and we also have a lot of capability in how you integrate models into larger systems, including energy markets at the national and global scale. And finally, it can easily be overlooked, but I don't want to. Is in program execution and integration. And so it's a tremendous skill set, actually our largest in terms of headcount of federal employees of any of these core competencies are those that know how to manage projects from a technical standpoint, from a regulatory standpoint, as well as in execution. And so it really does take a unique skill set and a powerful skill set to be able to be fiduciarily responsible for taxpayer money and ensure that external projects are moving forward and not wasting our taxpayer money. And so we have a set of goals to try to achieve in fossil energy, and we want to make sure that our project portfolio of 900 projects actually is moving in that direction. So our our Research and Innovation Center, RIC, is our in-house research arm, housing the 5 of the 6 core competencies as shown here. And so this federal staff plus our contractor staff that's supported through our site support contract really does pump out a tremendous amount of intellectual capital, intellectual property, as well as technology development. And that's an interface that historically Carnegie Mellon has interacted with, historically called Office of Research and Development, ORD, and now Research and Innovation Center. And so I do need to give just a quick update on the research site support contract. It was announced to be awarded last year. It was executed December 31st of 2018. Was the first full day of Leidos being the prime on our research site support contract. And you'll see regional universities, including Carnegie Mellon, North Dakota, Oregon State, Pitt, WVU, are contractors or subcontractors with Leidos on this research site support contract. This particular vehicle, and I'll call it a vehicle, is a way that we have our mission that we want to execute. We have our goals in technology development in the Inhouse Research program. And one of my biggest priorities is diversifying the applications to which we apply those core competencies. And there's a reason why I do this talk in this order, because we have skill sets inside the laboratory and with our partners under the research site support contract, that those skills can be applied not just in the fossil energy application space. I gave the example in geosciences. We have examples in every core competency that I could give, and having this vehicle, this research site support vehicle, gives us access to partners with a tremendous depth and breadth of skill sets that can partner with us at the laboratory across the entire energy space. And so that is what this vehicle is used for, and it's a tremendous opportunity for us to move forward. And so I know the folks in the Scott Institute here are working with Leidos, and you know, it's really about providing an opportunity for us to be able to tap into the skill sets that exist at our partners. And so we're excited to have this. I want to now spend some time, and unfortunately I was hoping there was a clock here. I need to keep a check on my time. But I want to run through some examples of some research areas that we've really had a priority or a set of successes. And one is ineffective resource development. If you know the history of the development of unconventional hydrocarbons, hydraulic fracturing, and directional drilling and coupling those together has resulted in the unconventional natural gas or shale gas revolution. That technology was pioneered at NETL 30 some years ago, and took some time to deploy into the market and achieve its learning curve, cost efficiency benefits. Well, as we started looking forward, we are still working on understanding the unconventional resources through characterization, understanding recovery rates, and we do this both in-house and with our research partners and external partners. We have a number of field sites around the U.S. that we're gathering data from, and we'll use this to apply our big data machine learning analytics to, as we're able to put together data sets that often may not exist or cross-cut different basins that they're able to do in industry. And so this is one real area where we are focusing not only on recovery and mitigating impacts, environmental impacts associated with production, but looking at innovative and new technologies, a couple of which have already been deployed in the field in this region that were developed under the NETL portfolio. And so to dig down into one specific area is looking at the way that we deploy seismometers to measure microseismic events in the subsurface, how we distribute the geophones, as well as fiber optic distributed acoustic cables, so that we can better ascertain stimulated volume. And so if there are some, I know there are a couple of geoscientists in the room that you're familiar with where I'm going there, but the key is that we're trying to take and gather as much data as we can about what happens in the process under the subsurface to maximize the amount of recovery. Some argue that we're at 10% of the hydrocarbons actually being recovered from a stimulated volume, but that all depends on what your denominator is. We're trying to understand what the denominator is, how much is there, and how we can improve the recovery to minimize the level of impact. If you get 8 times as much gas out of the same surface well, then you've divided your surface disturbance by 8 when you're factoring in on the end use of energy. And so that's where we're going in terms of the goals. The second major area is in efficient energy conversion. And so again, the more efficient we can become in how to convert energy from its primary source, be it coal or natural gas, into the usable energy, the electron in your vehicle or in your iPhone, the lower the environmental impact. So some specific areas are how we can improve performance of materials that are working in extreme environments. In extreme environments, a boiler tube in a coal-burning power plant sees temperatures and temperature gradients that many other materials don't. And so if you know the second law of thermodynamics, the higher you can push the temperature at which you convert electricity, the more efficient you are. And of course, there's a denominator there too. If you, the lower you can push the rejection temperature, again, back to efficient use of water. You couple those two things together and you can increase the efficiency of the existing fleet of coal plants by a tremendous amount, reducing their environmental impacts. And so if you don't know, the most efficient coal-burning power plant in the Western Hemisphere sits between Pittsburgh and Morgantown, the Longview power plant, and we have a number of interfaces to work with Longview on how we can take that example of a power plant and deploy it more efficiently at a lower cost around the globe. The second example is using optical fiber sensors in that production chain. Everything from, I already mentioned, a distributed acoustic sensor in the subsurface, but also how we can develop more efficient fiber optic sensors and ones that work in more extreme environments that can actually be deployed in power generation as well as in the subsurface. And so that we have some unique capabilities of being able to build those and extrude those fiber optic cables at NETL. A third broad area is in environmental sustainability, and this really cross-cuts every program that we have, is how we're become more environmentally sustainable. It's everything from responsible water and power generation, how we reduce the amount of freshwater impact that we have on generating electricity, as well as developing carbon capture technologies. And these carbon capture technologies span the range of liquid-based, amine-based carbon capture technologies to solid sorbents, as well as membrane opportunities. And membranes require a very large driving force, and then you start examining the ways that you can couple membranes as the first cut of CO2, and then use other types of sorbents to get us below a 90 or 95% capture threshold. And so this initiative, called the Carbon Capture Simulation Initiative, CCSI, I know CMU was heavily involved, historically heavily involved, and continues to be in CCSI. It has a real goal of being able to use models and simulate processes all the way through systems in a way that we can lower the cost of deployment and lower the timeline of deployment of new technologies. There is a huge inertia and a huge barrier to new technologies moving into the energy space, particularly in power generation from coal, considering we haven't built a new coal plant in the United States since 2011, that one actually being Longview. And there's a real barrier for us to get things into the market. And so CCSI not only is focused on accurate unit-based modeling, as well as ways that we can start jumping over deployment timelines that often can range in multi-decadal timelines. And then, as you can possibly pick up through here, a lot of technology that's woven in is about computational science and computational research. So it's everything from computations of material science that go from DFT calculations through larger scale coarse grain calculations, device engineering when you start weaving in computational fluid dynamics, as well as other more detailed device engineering, through data analysis and machine learning. There's such a focus on computational science at NETL. that we have now, with an act of Congress, have funding that we have built a supercomputer on site and refreshed it that was commissioned earlier this year. Users have been using it since sometime in January. It's the 23rd fastest supercomputer in the United States and 52nd in the world. And we're still working with the vendor to make some efficiency improvements and possibly adding on, expanding it a little bit. This supercomputer did not take very long for us to reach 100% utilization, and we anticipate keeping it that way over the lifetime. We'll have 5 years of it right now. And so Joule is physically in Morgantown, but we've got pretty fast data connections between Pittsburgh and Morgantown. And then finally, in this kind of capability space is in our machine learning and data analytics. We have a Center for Data Science and Machine Learning that we're in the process of bringing online over the next few weeks. Hopefully, we're pushing the vendor to hopefully it'll be in the next few weeks. Depends on what few means to you. But that facility is in Pittsburgh on the research ridge. Will be a great resource, both in-house and with our partners and really across the Department of Energy space, where we can actively develop and deploy new artificial intelligence and machine learning algorithms and develop those algorithms on real large and big data sets. So right now we're only at about 8% full in terms of our data storage capabilities, and the way that we have integrated data storage, data acquisition, and machine learning is really in a unique machine learning environment. And then one example I'd like to highlight in terms of successes of in-house research in the computational science area leverages off of our supercomputer Joule because of the computational intensity of ab initio or molecular scale atomistic calculations. And so some of our researchers in Pittsburgh, led by a group with Chris Matranga and some others I know has worked with CMU, we're working on a reduction catalyst for CO2 using some interesting alloys of gold and copper nanoparticles, all simulated in silico to be able to optimize that CO2 conversion reaction. And this particular alloy that's developed in silico has an activity and selectivity with about a 50% reduction in precious metal content, so we can reduce, not only provide reaction activity, but also reduce the cost of the catalyst itself. So this high-level success, there's more detail in the JCPC paper if anybody wants it, and we'll have these slides distributed for you because I'm going to speed up really fast now. One real big area of a win I mentioned was the MFIX model, which is our computational fluid dynamics model. Recently has been modified to MFIX EXA to be able to take advantage of exascale computing and our supercomputer capabilities both at the lab and around the globe in the DOE complex to be able to simulate more accurate computational fluid dynamics models, including multiple fluids, 2 fluid models, as well as a couple other different types of multi-fluid, multi-phase flow modeling capabilities. And one example that I wanted to highlight is, I believe it started last year, some work with the Environmental Management Office in the Department of Energy with a reactor in Idaho that's specifically called the Integrated Waste Treatment Unit. That's a radioactive liquid processing unit in Idaho that was having some trouble in startup and achieving fluidization within the reactor itself. And we were called upon at NETL to help and assist EM, Environmental Management, on coming up with a design and testing and being able to get this reactor up and going. We ended up saving about $10 million in testing the whole complete suite of range of operating conditions to achieve fluidization, and saved about $100 million of additional cost through computational fluid dynamics of starting up the reactor and delays associated with that. And so just one success story of how we can apply computational fluid dynamics to real world problems. Another example of a project that we've been working on really on and off over the last 15 years or so is being able to design a long-term methane hydrate production test. Methane hydrate is a potential source of natural gas, prevalent in offshore as well as in the permafrost and the Nankai Trough in Japan, has yet to see a long-term test longer than 15 days of production. And so with a collaboration with the U.S. Geologic Survey as well as partners on the Alaska North Slope, in December, just between Christmas and New Year's this year, completed a hydrate test well on the Alaska North Slope that did clearly identify this location as being the best location on the globe to this point identified for a long-term production test. And so that last week there were meetings about how we move this forward into a full long-term production test. But this was the confluence of partnerships in academia, industry, as well as other national government agencies, including and most notably the U.S. Geologic Survey, on being able to use predictive models to predict the resource of hydrocarbons in the subsurface. This site was previously not drilled. NETL and USGS had interpreted this as being a prime location, and then in December when this was drilled, in fact, did isolate and locate a number of hydrate deposits at temperatures not yet seen in a test well around the globe that will present a tremendous opportunity for designing and developing a long-term production test for gas hydrates, really moving forward that technology globally through this project. And that one I'm not overstating at all. This is the leading project in the world in hydrates. So we have four primary technical initiatives that I'd like to highlight again as I move forward toward the end, is in how we can develop high-efficiency, low-emissions power generation. And one example of this is the Coal First initiative I mentioned before. And then second, in how we integrate and optimize simultaneously the nodes on our electrical grid, the nodes being the power generation stations across our grid, with the way the grid is now operating in a more dynamic mode and will continue to be increasingly more dynamic in the future. Thirdly, how we can affect real-time decision-making in the subsurface using the data that we acquire. And so this includes how do you take logging, as a specific example, how do you take logging while drilling data to inform where your drill bit's going to move so that you optimize your recovery in the end, and how we make real-time decisions in the hydrocarbon space as well as in CO2 sequestration. And then fourthly, and again, these are just some examples across a 900 project portfolio of how we then add high-value carbon products from our domestic coal back to coal beneficiation, and how we can use this resource to develop new and high-value products. So in high efficiency, low emissions power generation, our focus areas are to reduce the time to design, construct, and deploy the power plant through CCSI and some other initiatives, how we minimize the water consumption, as well as criteria emissions, as well as carbon capture. And so when power plants are deployed or we retrofit the existing fleet, how can we meet these three criteria in these focus areas, including how do we integrate with energy storage on the grid, how do we integrate with what's called coal upgrading, as well as enhanced value stream realization of potential products. And then finally, how can we have a grid that uses optimally its existing capital that's on the grid with the changing grid dynamics. There is a real impact on taking something that's intended to run at steady state and operating in a dynamic mode. And so back to that example called first, flexible, innovative, resilient, small. I said sustainable, small. Sorry, small and transformative, and a set of specific design criteria. So that RFP has been on the street, the responses are in, and so sometime in coming months you'll see the results of that particular RFP and projects that will be moving forward to design the coal plant of the future to be flexible, innovative, resilient, small, and transformative. In the area of optimization, integration, optimization, and resiliency, if we focus specifically on some stress points within a power plant of how these power plants can begin to be more integrated and resilient within the grid, we can see that, well, one big one is difficulty ramping up and down to follow load. So you don't take a coal plant and you don't load follow. That's why we have natural gas peakers and other things. But can we, in fact, create flexibility within the existing grid or a future grid so that we can ramp up? And it takes a number of things. It takes materials reliability. How do you design materials that operate in an extreme environment and take temperature and pressure, and those are two extremes, but then add ramping and load following and variable flows, and that adds a whole other level of complexity that is difficult for materials to withstand. That includes how you can have fatigue failures in various components of the power plant. And so we are actively working on both real-time sensors that can measure corrosion in real time, in situ, as well as material fatigue and stresses on those materials so that we can predict failures. And so this is a very specific operational example. If you're operating a power plant and you can measure and predict when you're going to have failure on a piece of equipment, you can plan an outage, shut it down, and repair that piece, as opposed to waiting for a failure and then having what's called a forced outage. And so that's where a specific example of some improvements to be done. And also on the turbine blade, this is a common problem, steady state or dynamic problem in terms of corrosion and erosion on turbine blades, to where we're looking at improvements, and historically have achieved many improvements in turbine design and manufacturing, including being able to 3D print components to provide enhanced cooling across the entire turbine blade. So just some specific examples on this area. So I wanted to show an example of some in-house research that we have going and trying to completely change the paradigm in which we make electrons from a fossil fuel. And so this paradigm, if you're familiar with how you build a power plant, be it natural gas or coal or nuclear, you use your fuel, you heat up water, you heat up steam, you run the steam through a turbine spins the generator makes electrons, in a nutshell. Then you have a cycle and you cool it down and you create a Rankine or Carnot cycle. But what if, instead of operating that turbine under a pressure drop, so can we do something what's called pressure gain combustion? Can we combust in a fixed volume, which increases the pressure, and in fact then achieve higher efficiency through what we call pressure gain combustion? Now if we do that, we think of, well, the internal combustion engine doesn't operate at fixed volume, although ignition occurs right after you end up with the most compressed fluid. So if we design a system that takes very strong controls and basically has hundreds or thousands of internal combustions in a fixed volume over time with lots of control, can we then increase the pressure during combustion and release that pressure at higher temperature, creating a more efficient engine that can then, this rotating can actually be, can still rotate a shaft and rotate a generator, however you want to do it. So we have a rig in Morgantown on site doing this pressure, or two experimental rigs actually doing this pressure gain combustion, which is really a unique capability. There are a couple partners on these projects, including Aerodyne. I think Aerodyne Rocketjet is a partner, and we're starting to see the confluence of simulation, showed here on the left, with real experimental values. And so you see two combustion fronts here when you see one here. Often, what we see in an experiment is you can actually jump phases and can in fact create either two combustion fronts or one combustion front. But we are seeing the convergence now of modeling capabilities with experimental results. What that leads us to is once you can accurately model, we can come up with better and better designs once we understand the fundamentals of what's going on. And that's the stage we're at now. Another very interesting, very forward-looking project we have in this particular area of next generation, it's called direct power extraction. Does anybody remember MHD or know what MHD is? I figured these are the two I thought actually fine. And so there is a legacy program, and what's called MHD, magnetohydrodynamics. You can actually create an electric field without moving a generator. And so we have a new experimental rig in Albany that is a non-seeded plasma that can, in fact, pass through a magnetic field, create a flux, create electricity without actually spinning a turbine. And so I'll leave it at that in a nutshell. But again, this is an example of modeling capabilities converging with experimental capabilities where we can start moving it forward beyond the legacy MHD program where we can design for carbon capture, we're doing simulation and validation, and we've made some advances in the plasma. Now, the direct injected plasma as opposed to a seeded plasma, just to give you some details if anybody is interested in MHD. In the real time, I'm running long, so I'll be quick. We'll be quick here at the end. I mentioned real-time decision-making in the subsurface, and this is specifically about being able to take a wealth of data that flows in, and just so you know how fast data can flow in, at our experimental site, the Marcellus Shale Energy Environment Laboratory, when it was operating in real-time data acquisition, we're talking about at times a terabyte an hour of data over months. And so when you think about that amount of data, it's impossible for a human to do it. And so what we're designing and building is the opportunity to take the combination of national level data, regional level geologic characterization, stress data, as well as lithography, bring it down to the local level and stress changes associated with hydraulic drilling and fracturing, as well as at a specific well site, the real-time data that's coming in from acquisition of microseismic technologies, as well as what we're seeing at the well, the drill bit and logging while drilling, and being able to put and layer all of those data layers together to be able to predict how we can more efficiently and more effectively produce hydrocarbons. So that's one example in the machine learning space. More generally, in real-time decision making in the subsurface, part of it is integrated assessment. Imagine, just it was mentioned, Anna mentioned in the bio, my work with the Macondo well, the BP oil spill in the Gulf Coast. But imagine if we had the tools at our hand to where in real time making decisions during drilling, during cementing in that case, we were receiving the data that we could use to make decisions that involve human safety, that involve oil spills, that involve being more efficient in producing by making decisions as we're drilling a well or as we're producing that can achieve better outcomes. And that's in a nutshell where we want to go with real-time decision making in the subsurface, as well as when we're storing carbon dioxide, that we can have algorithms that use artificial intelligence and machine learning that as data come in that we might not notice as a human factor, but can start to predict the effects of CO2 fluid flow or CO2 leakage to reduce and mitigate the risk of storing CO2 in the subsurface. And so that's where we're going there. There's a number, we can improve the resources recovery in the laboratory and in simulation, enable it through bringing together field data and reduce order models, and minimize it through minimize impacts through high performance computing, as well as having that robust data set at your fingertips that you can reach into and be able to learn from. And then I think it's the final example is how we add value to our coal as a starting point for manufacturing, as a starting point for high value materials. If you're familiar with the research work of NETL over the last 20 years, you know that there was a whole carbon products effort. This has been reinforced and revitalized, or tremendous successes in how we make new products from coal. But now as we look at the future of carbon-based materials, including nanomaterials, whether it's in nanowires, nanofibers, carbon fiber reinforced plastics that now are a third the weight of steel and twice the strength, there's a tremendous opportunity to take our fossil fuel resources and add value to them into our value chain. And this includes in fuels and consumer products, as well as how we coke our carbon products and make steel, as well as certainly electricity. But there's a tremendous number of other manufacturing processes that can make, as I mentioned, plastic composites and storage materials, 3D printing materials, the types of materials that we use in the future of manufacturing. And so one particular example, imagine we take a $30 to $60 per ton coal feedstock, can use some classical coal processing technologies and make products that in fact are $70 million a ton if you were to make a ton of it. And so these include graphenes and inks and these processes of using a really good carbon resource to make carbon-based materials. There is a tremendous opportunity to go from $30 to 70 million. And so the last bit I want to highlight, and I know we have a little bit of extra time for questions, which is great, is how the laboratory wants to partner. And I'll say that is truly our desire, our mission, and a priority for us, is not only partnering in the traditional sense of, well, we manage a very large portfolio of Department of Energy funds, we put on the street funding opportunity announcements and RFPs. That way I'm pretty confident the faculty members are aware of. We want to partner through our in-house research program. It is one big priority of mine, and Randy Gentry, if you get an opportunity, Deputy Director for Science and Technology, here with me, for us to grow our in-house research capabilities and do it in conjunction with our partners on our research site support contract. But then there's another way, and that is through tech transfer. We are a conduit of technology development, and we develop our own with our partners. And so we are, in fact, focusing a lot of effort on how we partner with outside groups and we push forward and commercialize technology. And I'll go back to that one key word I wish that you would remember is impact. How we can create impact, how we can move things into the market and commercialize. And so it is our role as a national laboratory, since we don't have Bell Labs around anymore, we don't have those other examples. Industry is increasingly cutting and slashing their research budgets and their research arms, that it is critical that the Department of Energy and national laboratories start filling the gap between where universities have a lot of effort in technology readiness levels 1 to 3, if you want to be specific on a TRL definition, and then industry doesn't want to touch it until it's, some industries 9, some industries don't want to touch it until it's TRL 6, where you've already prototyped it, you can demonstrate, and they'll take it and scale it up, but somewhere in that gap is where the national labs will play, and we own that responsibility. And so this is where partnering both with our industry stakeholders that create the demand side pool and allow us insight into what the future markets can be for new technologies to go into the market, with universities that have the wealth of ideas of early stage technology development, and then how we can marry industry and Department of Energy and national labs to ensure that the best technologies are going into the market, so that we have that income or that outcome, those impacts on the future of our energy portfolio. And so we have, this is just our icon soup of a few examples of our partners we have in large and small businesses and academics, as well as across the U.S. government. And so we, being the national laboratory in this particular region, own a mandate for us to have impact on the regional economy of Appalachia. At Appalachia, Western Pennsylvania, through, until we start stepping on Oak Ridge's toes. That we want to own our role as a convener and as a catalyst in regional economic development for this region. And this region, historically and today, still relies on energy as a base for our economy. And so that is truly our role, is to bridge that gap, bring industry to the region, bring industry to partner, bring the ideas out of academia, and for us to be that convening partner. So one particular example, it's not a regional one, but it's how technology had matured under our watch for work in the early 90s and proof of concept for initial carbon capture, all the way through the TRL levels, up through finally now full-scale commercialization project in Petra Nova that I think to date has sequestered over 4 million tons of, I think it's 4.6 is the last number if I remember right, million ton, of CO2. It's the largest commercialization of CO2 capture and sequestration in the United States, and it truly led from the early concept of technology development through scale up and then government partnership with NETL and NRG to commercialize this technology. And this is an example of what we want to see happen over and over again. And so the way that we do that, the toolbox that we can partner with, I've mentioned FOAs, you're familiar with those. We have a number of technologies that can be licensed by industry. Probably not that constituency in here. But there are a number of tools in our tool set for us to work together, not just transactionally, but to truly develop partnerships. And so right now we're working on how we partner with CMU through a couple of vehicles, certainly RSS, but also ways that we can create cooperative research and development agreements, intellectual property agreements, memorandum of understanding. All of these things are at our fingertips, and we're committed to making sure that we have the right vehicles to partner in any way possible. So I hope I left some time for questions, and thank you very much.
We ran a little long, so we don't have time for many questions, but one thing I'll say before I take a handful is that one key person who's not in this room is Andy Gelman. He's, those of you who've been around know that he has historically managed the CMU-NETL relationship. He's at a Gordon Research Conference today. He regrets not being here, so his absence is not intentional. In fact, he had a teleconference earlier today with both of these folks. So
I've known Andy for 13 years.
Yeah, exactly.
I wouldn't have taken it personally.
Andy is he's deep in all this. It was his absence is conspicuous. I just wanted to reassure people. So anyway, question.
Yeah, just real quick, despite impressive the portfolio, I have a key question there on the AOC turbines. You mentioned that you 3D print the cooling channels. What's the TRL level on that 3D printing?
Well, actually, I mean, Siemens and GE are their newest. So the question was, what's the TRL level on 3D printing of turbine blades? And in fact, Siemens and GE are 3D printing their natural gas combined cycle turbines today. And yeah, it is truly impressive.
Thank you.
Other questions, really quickly. Yes.
Correct me if I'm wrong, but I thought that natural gas had a lot of advantages over coal. So what does this coal first power cost for a similar natural gas reactor?
Well, and so if you didn't hear the question, there are some. He was under the correct understanding that there are some advantages with natural gas in terms of power generation. And part of it's just chemistry, CH4 versus what is roughly C1H1 for coal. So there is inherently a lower carbon footprint and fewer what would end up as criteria emissions for natural gas. So in terms of technology development, though, in the United States, our available resource and the cost point of that resource is still at a point where if we can develop technologies for coal, for carbon capture from coal and ensuring the lowest emissions possible, where having both options at our fingertips is the best option moving into the future. In terms of carbon capture, that's the one area where natural gas is a bit of a disadvantage, and it's simply because the natural gas flue gas stream is lower concentration of CO2, which is in one side a good thing, but for capture it's not a good thing. In terms of your ability to capture on a pound for pound basis. And so we develop technologies that can work in under the emissions conditions of coal as well as for natural gas. We're working on the efficiency of how we produce as much natural gas at the lowest environmental footprint possible, and then develop technologies that can capture from the flue of either one. And so that's where we are now. Now also, a lot of it's driven by the budget that is given to us by Congress in terms of the portfolio itself. And so there is a line drawn in the sand from Congress of money that goes to coal research and money that goes to natural gas research, and those are the priorities of Congress right now in terms of the blend of our portfolio.
Yes.
Excuse me. Hi. I work in the Technology Transfer Office here at Carnegie Mellon, so I'm curious how being a government-owned, government-operated lab affects your ability to spin out companies either by your own researchers or by your contractors.
Well, and so I mean, for the contractors, it just depends on the flow of IP and the fact that technology developed by federal employees employed by the U.S. government is under a few different rules than technologies developed by somebody in the private sector or academic sector. And so those rules, we work within those constraints pretty readily. That is a priority, I know both mine and Randy's, is that we not only use the available tools that we have for tech transfer, But if there are barriers, I'm not opposed to telling people in Washington that those barriers are restricted for us as a go-go. And so you can see there's some language that's already been proposed in Congress that might actually give us another tool in our toolbox as a government-owned, government-operated Department of Energy laboratory. And so I'm not advocating for that one. The jury's still out internally whether it helps us the best or not. But there are mechanisms by which we can work within the existing constraints. So that being kind of this general fluffy answer. The specific answer is we're committed to it. We'll make it work. And that's what I just want to say. We're working and continually working with industrial partners and academic partners on how we can come up with the right tech transfer mechanisms and relationships and agreements, the way that we can flow intellectual property, the way that's mutually beneficial. We'll work within our constraints, and we'll also try to make them less constrained if necessary. I don't know if that answered your question.
Anything else? There's a 5-10 minutes sort of time still. I encourage you, we'll break now and we can have some informal time for a handful of folks to come up and talk one-on-one if you'd like. Otherwise, thank you all for coming and we'll see you next time.